Now that we've identified this phenomenon of continuity, you probably realize that most functions that we work with are actually continuous for most x values, or most input values. So it's nice to have some vocabulary to describe the phenomenon of being continuous not just at a single x value, but at lots of x values. So we'll say that a function f of x is continuous on an entire interval if f of x is continuous at every x value that's in that interval. Additionally, we'll call a function continuous if it's continuous everywhere on its domain. So since, graphically what this will look like is, if some function, if we have this interval from a to b in mind, as long as you can draw the graph from a to b without lifting up your pencil, that means it's continuous at every x value in that whole interval, and so it's continuous on the entire interval. Most graphs that we draw are made up of a few pieces like this that are just, one curve, and so pretty much all of the graphs that we ever look at are made up of just a few continuous pieces. Let's look at some examples of common types of functions that have continuous chunks like this. So first of all, what about polynomials? Well, we noted in an earlier video that for polynomials, no matter what x value a we're talking about, the limit of every polynomial is the same thing as just plugging in that x value. So that means that polynomials are continuous at every real number a. So that means polynomials are continuous. In other words, they're continuous on their whole domain. So yes, polynomials are continuous. All right, what about rational functions? Well, remember that for rational functions, we showed that they're continuous for all x values where they are defined. And, rational functions will only fail to be defined at a few x values, just a finite number of x values, possibly 0. So rational functions are continuous for most x values. And in fact, since they're continuous for all x values where they are defined, another way to say that is they're continuous everywhere on their domain. And that means that they're continuous. All right. You can see lots of functions are continuous. What about root functions? So here I'm talking about functions like square root of x or fourth root of x. Well, for these functions, if we take a limit as x goes to a of some nth root, one of our rules about limits says that you can move, as long as everything here is defined, you can move this limit inside the root, but then now this limit is straightforward to evaluate. Inside the root, it's just a. So as long as both sides here are defined, then this root function is continuous. So another way to say that is that root functions are continuous on their whole domain, so they're continuous. With possibly one slight little wrinkle, I guess. If n is even, so we're talking about an even root, its domain is actually just positive real numbers. And so whether you count it being continuous at 0 or not kind of depends on what you mean by continuous. So for all these x values over here, it's no problem. It's continuous, but there's a little wrinkle at 0 because it can't be continuous at both sides because the domain doesn't extend onto both sides of x equals 0. But if you allow one-sided continuity, so that being continuous just from the right, or the limit from the right is equal to the value of the function, then it's continuous even at 0. So whether that counts as being continuous or not depends on the context that you're working in. But certainly at x values away from 0, even these even root functions are continuous. All right, what about sums, difference, products, and quotients of continuous functions? Well, let's look just at sums. The argument for differences, products, and quotients are essentially the same. So let's suppose that f and g are both continuous at some x value a. Let's ask, what about the function f plus g? So let's find the limit as x goes to a of f plus g of x. That's the limit as x goes to a of the f plus g function. That's f of x plus g of x. But now we can use the sum rule for limits. So this is the limit as x goes to a of f of x plus the limit as x goes to a of g of x. Although we should be careful and check, right? The sum rule for limits says that we can do this as long as these individual limits exist and are finite. But they are, because f and g are continuous. So this first limit, the limit of f, is f of a. And because g is continuous at a, the limit of g is g of a. But this is exactly the value of the function f plus g at the x value a. So the upshot here is, wherever these individual functions are continuous, their sum is also continuous. So that means sums of continuous functions are continuous. You can see the same argument is going to show that differences are continuous and products are continuous. Products of continuous functions are continuous. And quotients of continuous functions are continuous wherever the denominator isn't 0. As usual, you can't let yourself divide by 0. All right, so sums, differences, products, and quotients of continuous functions are all continuous as long as they're defined. What about compositions of continuous functions? Now, to really prove something about compositions of continuous functions, you actually need the sort of precise technical definition of continuity, which we haven't really looked at yet. But it should seem plausible, at least, that if you take the limit, or if f is let me write it this way. If g is continuous at a and f is continuous at g of a, then if we imagine taking the limit as x goes to a of f composed with g, so there's our symbol for composition. So f composed with g of x, that's the limit as x goes to a of f of g of x. Well, as x goes to a, right, so this x is heading towards a, but so what's happening inside here is that we're getting the limit as x goes to a of g of x, but g is continuous at a, so this is g of x. So the stuff inside here is going to g of a. So the stuff inside the function f is going to g of a. But if f is continuous at g of a, then that means that as the inside goes to g of a, the value of the function should go to the same thing as if you just plugged in g of a, so f of g of a. All right, so if you have a composition of continuous functions where the outside one is continuous at the value at the limit of the inside one, then the composition is continuous. Now, this isn't a precise proof, so I hope it's somewhat convincing, but it's not a totally precise proof. But there is such a proof, so even if this doesn't convince you, compositions of continuous functions are continuous. For one more example, right, there's one more big collection, one more big type of function that we often work with, the trigonometric functions. So let's think about the continuity of trigonometric functions. Now, it turns out to figure out the continuity of trigonometric functions, we only need to worry about sine and cosine, because all of the other trig functions are quotients of sine and cosine in various arrangements. So really, we just need to think about sine and cosine. And it turns out for sine and cosine, the hardest parts to figure out are just at 0. So let's ask, is sine continuous at x equals 0. Okay, well, where does the sine function come from? Remember, the sine function, if you have a unit circle, the sine function, and you have some angle in here, the sine function tells you the height of this point up here. So the length of this line segment is sine of x. And that's when the angle in here is x. And this has to be measured in radians. So here x is in radians. Well, if you're measuring x in radians and we have a unit circle here, the arc length here is actually x. So we have this vertical line segment that's sine of x, and we have this arc to its right that has length x. But that means that sine of x has to be less than x, or less than or equal to x. Also, sine of x, as long as x is greater than or equal to 0, sine of x, and I guess less than, or let's say less than or equal to pi over 2, sine of x, as long as we're in this range, sine of x is going to be greater than or equal to 0. All right, well, you can see we're kind of headed for a squeeze theorem kind of situation. If we now take the limit as x goes to 0, I guess we're taking the limit as x goes to 0 from the right because we have these x values. Well, the limit of 0 as x goes to 0 from the right is 0. The limit of x as x goes to 0 from the right is also 0. So by the squeeze theorem, the limit of sine of x as x goes to 0 from the right is also 0. So the limit as x goes to 0 from the right of sine of x is 0. A similar argument shows that you get the same limit if you take the limit from the left instead of from the right, so we can actually say the two-sided limit here. All right, so we know the limit as sine goes to limit of sine at 0. Notice that 0 is sine of 0. So this says that sine is continuous at 0. Well, what about cosine? Well, cosine, for x values near 0, cosine of x is just the square root of 1 minus sine squared x. And then we can use the limit laws, right? Here we have a root of a difference of a square of a continuous function. But all of these operations preserve continuity. That's what we noticed just a minute ago. So cosine is also continuous at 0. All right. So now we know that sine and cosine are both continuous at 0. What about other x values? So now let's ask the real question. Is sine continuous at x equals a? And a could be any real number here because the domain of sine is all real numbers. So what we need to do is calculate the limit as x goes to a of sine of x. And it's not really clear how to proceed. I mean, it seems like somehow we should use the calculation that we just did. Somehow we should use the fact that sine is continuous at 0, but it's not really clear how to use that fact. Well, there's a nice trick. Right? X is going to a. It would be nicer if it were going to 0 because we know something about the continuity of sine at 0. So what we can do is rewrite the insides of this function, write it as x minus a plus a. Right? X minus a plus a, that is x. So, this really is the same thing as what we started with. But now that we have a sum inside of our sine right here, we can use the sum identity for sine. So the sum identity for sine says it's sine of the first one, x minus a, times cosine of the second one, plus cosine of the first one, x minus a, times sine of the second one. Okay. But now we can use the sum and product rule for limits. We get the limit as x goes to a of sine of x minus a times the limit as x goes to a of cosine of a plus the limit as x goes to a of cosine of x minus a times the limit as x goes to a of sine of a. Okay. Well, for this first piece, notice that we have a composition here, right? Because we have a sine function, and inside of our sine function is another function. And x minus a, as x goes to a, x minus a goes to 0. So here we have a composition of functions, and the outside function, sine, is continuous at the limit of the inside function. But that's our fact about compositions of continuous functions now tells us that the limit is the sine, or is sine of, right? We can just plug in the limit of the inside part, so sine of 0. All right, now limit of cosine of a, well, a is a constant, right? X is the variable. So cosine of a is actually a constant because it doesn't have x in it, and the limit of a constant is just the same thing, so cosine of a. Plus, now this cosine limit here, by exactly the same argument as for sine, this limit of cosine of x minus a is just cosine of 0. And then the limit of sine of a is sine of a, since that's a constant. Okay, now sine of 0, that's 0. So who cares what cosine a is? Plus cosine of 0 is 1 times sine of a. So this whole thing turns out to be sine of a. And remember, what we started with was the limit as x goes to a of sine of a. Sorry, sine of x. So this shows that sine is continuous for every real number, right? Because this calculation, we said at the beginning that a could be any real number. So this shows us that sine is continuous for every real input. Right? All right, well, if sine is continuous, cosine is in some quadrants, so depending on the quadrant here, cosine is either plus the square root of 1 minus sine squared, or in other quadrants it's the negative of square root of 1 minus sine squared. But whichever quadrant you're in, right, all of our earlier facts about continuous functions say that this combination of a continuous function is continuous. So cosine is also continuous on its entire domain. Now, since sine and cosine are both continuous, that means quotients of them are also continuous. So tangent, secant, cosecant, and cotangent are also continuous on their entire domains. So all of the functions that we commonly work with, there are two exceptions. We actually haven't talked about exponentials and logs yet, which we will later. But for all the other functions that we usually work with, they're all continuous wherever they're defined. Their only discontinuities are at gaps in their domain. Let's look at a few examples. Okay. So let's find the largest interval containing 0 where tangent x is continuous. Now we know that tangent, since it's a trig function, it's continuous at every point in its domain. Right? Just for a real quick sketch of the graph of tangent, it looks like this, right? And it has these vertical asymptotes. And the vertical asymptotes are gaps in the domain, so these are discontinuities. So to find the largest interval containing 0 where tangent is continuous, well, x equals 0 is right here. So how far can we go from x equals 0 and still have a continuous part of the graph? Well, we can go up this way, but we can't cross this discontinuity, right? Because we want an interval where this function is continuous. So we can't include this discontinuity, and this discontinuity is at pi over 2. And then starting over at 0, we can go leftwards, right? This is all a continuous piece of the graph, but we can't cross this discontinuity over here, which is at minus pi over 2. So the largest interval containing 0 where tangent x is continuous, that's between these two x values. So it's going to be from minus pi over 2 to pi over 2, not including the endpoints of this interval. So I'm using round brackets and not square brackets, because remember, square brackets on an interval indicate that you're including the endpoints, and we are not including the endpoints. All right, for one more example, let's ask about the continuity of this rational function. So is it continuous on this interval from 0 to 10? And is it continuous full stop? Well, this is a rational function, so the answer to the question, is it continuous, is yes. Right? By continuous, we mean, is it continuous where it is defined? And we know that rational functions are continuous where they're defined. So now let's look at the interval from 0 to 10. Well, for rational functions, they're continuous wherever they're defined, so what we should figure out is, where is g of x not defined? Well, a rational function is undefined wherever its denominator is 0. So let's figure out where this denominator is 0. We need to know, where is this denominator, x squared minus x minus 6, where is that 0? So let's set it equal to 0 and solve. Well, this one happens to factor. This is x minus 3 times x plus 2. So that means x is either 3 or 2. Now remember, the reason we were solving this equation was because we were figuring out where is g not defined. So g is not defined at 3 and at minus 2. Okay. Now back to the original question. The original question was, is this function continuous on the interval from 0 to 10? In other words, is this function continuous at every x value between 0 and 10? Well, clearly not, because we just said there's a discontinuity at 3. So the answer to this question is no, because there is a discontinuity at 3. Okay. So we've answered both of these questions, but the reason that I paired these questions together is because I wanted to point out this little peculiarity about how we use the terminology for continuous, or for continuity. We say that this rational function is continuous because it's continuous on its whole domain, but that doesn't mean it's continuous at every real number, right? It's not continuous on this interval, even though it's continuous. So you have to be a little bit careful about how you use the terminology surrounding continuity. Just because, right, asking if a function is continuous, you're specifically only asking about continuity where it's defined. So wherever it's not defined, of course it's going to be discontinuous because it's not even defined.